Thanks very much for attending my talk. Today I will present our paper, Touch While Before Use, Intuitive and Secure Authentication for IoT Devices. This is a joint work with my collaborator Xiaopeng, Feng Yao, and Dr. Zeng and Dr. Luo. We are all from the University of South Carolina. Recent years have seen a faster growing of Internet of Things. Many devices could collect privacy-sensitive information and raise security concerns. These devices also can be physically accessed by many people in a smart home or other clouded environments. So the operations on these IoT devices should be effectively authenticated. For example, some household devices can be accessed, can be operated by parents, but not the children. Although authenticating IoT devices is important, it's also very challenging. First, many IoT devices only have few buttons or just one knob. So it's inapplicable to applying password-based authentication scheme. Second, the IoT devices are highly diverse in terms of their installations, shapes, size, and so on. So it's very difficult to design an universal approach that works all devices. Third, considering the requirement of a low cost for IoT devices, it's infeasible to use costly techniques such as fingerprint recognition. At the same time, we also observe that the existing approaches have various problems. For example, currently many IoT devices can be controlled through an app installed on your personal mobile device. That app can be modified to be used for authentication. Unfortunately, when the number of IoT devices become large, it's frustrating to find a specific one with the app in a bunch of devices. Detecting a user's proximity to a given device may be used for authentication. However, the proximity-based approach cannot tell whether the user really uses such a device. That means this may be resulting in unintentional authentication. For behavior biometrics, it's impractical to conduct user profiling for each single device. So considering the characteristics of IoT device, we think a good solution should well satisfy all of the following requirements. It does not depend on unusual interfaces or special sensors. It does not require hardware modification. No assumption about size, shapes, or installations. Also, the solution also, should be usable, reliable, and secure. To effectively authenticate IoT devices, satisfy all of the requirements we discussed above. The key insight of our approach is that operations on an IoT device are legal only if the legitimate user's hands moves it. Based on this insight, we design our system. First, the user wears a smart wristband to perform an authentication gesture on an IoT device. Then, the IoT device can detect a sequence of inputs at a specific time slot. Meanwhile, the motion sensors in the wristband can record the user's hand motion. Once obtained the two sequences of data, we analyze the data and compute a correlation score of these two kinds of information. If a high correlation score is achieved, it's very likely that user is legitimate. After surveying almost 100 IoT devices, we found that knobs, buttons, and small-size touch screens are the most widely used interfaces. So we focus on these three types of interfaces, but our solution should be also workable on other interfaces as long as the physical operations are involved. For knobs, the authentication gesture is back and forth twisting. For knobs, the authentication gesture is clicking the buttons for multiple times. And for touch screens, we require the user to perform zigzag swiping for authentication. These gestures are designed for authentication due to the following consideration. First, they are applicable to almost all IoT devices. They are easy to perform and distinct from our daily activities. Once an authentication gesture is performed, we can collect two sequences of data. Here we take a knob as an example. From the knob, we can have rotation data, clockwise or anti-clockwise. From the wristband, we have motion data. Can we compare them directly to examine the correlation? Unfortunately, the answer is no, because these two sequences of information are very different. To make the data comparable, we propose a novel solution to represent the data. Our solution is based on the occurrence time of abrupt direction changes during the device operations. We call them as key events. The back and forth twisting will generate a sequence of events corresponding to the direction changes. The direction changes can be from clockwise to anti-clockwise or reverse. We record the occurrence time of these events and obtain a time-step sequence. After processing the gyroscope data, we observe that direction-changing events corresponding to valley points of the gyroscope data. So from the gyroscope data, we can collect a sequence of the time steps corresponding to the local lowest value. Here in the graph, we use the green points to show the lowest values. Now we can compute the correlation based on the two sequences of time steps from the key events. However, the problem is that we cannot compare them on time step, one time step by one time step. They do not ideally match. This is because MU may miss capturing a few key events, and the corresponding time steps may not equal exactly. So we extract feature vectors from the time step sequence and train a machine learning classifier to compute the final correlation score. We evaluate our system in terms of accuracy and efficiency with the following devices. We also study the resilience to mimicry attacks and examine the impact of important parameters and also the usability. Due to the time constraint, I will only briefly elaborate. First, to show the accuracy of our authentication ROC curves, as you can see, we achieve a very high AUC value for all of the three types of interfaces. The major attacks of our system are real-time mimicry attack. We assume there is an expert who knows what information is critical for our authentication system. Even so, our experiments show that it's very hard for attackers to mimic the victim at the real time. We evaluated the performance of our model when testing devices are not seen during the training. We see our model trained on one device demonstrates a good transferability. We also test the feasibility of holding a smartphone to perform an authentication. So the wristband is not a unique choice for our authentication scheme. In conclusion, we designed the first secure and usable authentication method that works with a commercial of off-the-shelf IoT devices and does not depend on unusual interfaces. We propose a virtual sensing technique established on clock to sense and describe operations on IoT devices. We implemented a prototype. Finally, our experiments show that our system is not only accurate, but resilient to mimicry attacks. That's all. Thanks again.